So in talking about chaos, this has nothing to do with our class. This was just like because we were talking about chaos. You can take I cannot draw a fucking cup. So these are a bunch of like little buckets or cups just strung around a wheel that rotates with as little friction as possible here. And then you have a water supply. And the water comes down and you can control the rate with like a switch, you know. So you have like just a knob on the hose, right? The more you turn it up, the more water comes out, and you can control that. So here's someone rigged up, this is my favorite, because it's rigged from a bicycle wheel and styrofoam cups. And just watch what happens. And so what you're gonna see here is them slowly turning up the rate of water flow. And it's also really just lovely if we can get the sound. If we can get the sound, I said. So you see this like regular motion that you would expect. Right now they are right at a very critical water flow rate. So it's not just spinning. It's slowing down and almost thinking about it a little bit. Oh, the other thing is these cups have holes in the bottom, and so they're draining water at the same time. So there's this interplay between water filling them and water emptying them out, or water emptying out of them. But yeah, this is called the Lorentz water wheel. And so now you see it just changing direction completely. And what we're going to see is it entering an unpredictable state, a chaotic state, where the future motion cannot be predicted.
I don't know why that reminds me of bifurcation.
This comes from bifurcations, yes, exactly, yeah. Bifurcations, chaos never appears on its own. It's usually a cascade of bifurcations that lead up to a chaotic state, which is that shirt that I have with the tree.
See, I still can't figure out how that really.
I'll send you the video that I sent Lou.
Okay, please do.
But notice how it's starting to become more unpredictable. It's about to bounce back. So can you imagine like a beautiful one of these made out of wood and nice metal out of the front of the science building? I think that would be awesome. Anyway, this is an example of chaos right here. So Lou, this was this was the other example I was thinking about.
So follow a regular pattern?
It won't follow a regular pattern, yeah. For a lot of, so like when you start turning up the water, it will be regular, and then at some critical place, it will cease to be regular, and you won't be able to predict what it's going to do. It'll change. You can see how it's, it's really pretty wild what it's doing. Now it's like kind of just going back and forth. And this is like a very primitive rainy day project here. So that's pretty cool. Anyway, let me show you something else while we are here. I want to show you a video about the Riemann sphere, and then we can get on with our day. So I've got like a hint here on how to search for it. God knows I couldn't write down, send myself a link. I do have a new homework assignment up. Did you all get the email I sent over the weekend with like an extra problem to do? We'll start off the hour talking about that. Oh, here it is. Mobius transformations revealed. Okay. Oh yes, this is a lovely video. Hopefully we got some sound. Yeah, pretty.
Mobius transformations are among the most fundamental mappings in geometry, with applications from brane mapping to relativity theory. A Mobius transformation sends each point on the plane to a corresponding point. They're built from 4 basic types. The simple translations, dilations, rotations, and inversions, which turn the plane inside out. Lines on the plane either remain lines or transform to circles, and right angles stay true. In general, a Mobius transformation can be a complicated combination of all 4 effects. The true unity of Mobius transformations is revealed by moving into the next dimension. Taking a cue from Bernard Riemann, we place a sphere above the plane. A light at the top shines through the spherical surface, illuminating the plane. As the sphere moves, the points on the plane follow. When the sphere translates, so does the plane. Raising the sphere gives dilation. Spin the sphere like a top, and the plane rotates. Rotation about a horizontal axis corresponds to inversion. Even the most complicated Mobius transformations are revealed to be simple motions of the sphere.
Kind of illuminating, right? Like, no pun intended, but like literally. Yes, yes.
Does the sphere relate to what we were doing with the by pulling in all the infinity from on top of like,
Yes, that was the thing. Yes, that was the thing I was talking about at the end of the hour. Is that what you're? Yeah, cinching up like a purse string.
Yeah.
Yeah, like cinching it up around the edge. That's what my wife said when I was telling her about this. Like how cool it is. She'll take this any day over talking about crypto. So. Got like a very limited amount of crypto things I can talk about per day. Let's get that shut down. Cool. So, yeah, Labina, it's definitely exactly that thing that I was talking about last time, where we took the sphere and set it right above the plane. There's 0, and then there's infinity at the top, and each complex number z is mapped onto the sphere by taking a line from the North Pole, infinity, and projecting it onto the sphere. And that's a 1-to-1 and onto thing. Except it's not really 1-to-1 out at infinity, because up at infinity what we have is the line is actually tangent to the top of the sphere. So you have to imagine that it's out here somehow touching infinity. You can't really, because that, yeah, it's just too hard for our brains, but is that kind of like what you're asking, just to like, yeah. Cool. So, did anybody make any progress with that problem I gave you all? It was to warm up a little bit. That was just a warm-up problem. It's not homework. There is some homework up. So there's a homework assignment up on World Class. It's in the announcements, one little hand homebrew problem followed by some book problems that are probably involved, is what I'm thinking. I remember thinking that as I made the list. Especially the homebrew one. The homebrew one will be easy, but there's a deep question in it that I don't think will be easy.
I have enough homebrewing this week.
Yeah, did you actually literally homebrew?
No, I have to. I'm gonna do it tomorrow. It's the plan.
Alright, well, homebrewing and complex, I think it sounds like a pretty good Tuesday to me. Yes, ma'am.
Our last homeworks.
Oh, collect those.
Yeah.
Yes, thank you. Thank you, Lavina. If you have those. If you are ill, I'll get those from you Wednesday. Sydney, Nathan. Thank you. Many things. Oh, and a paper clip on top of it. Hell yes. Outstanding. Oh, thank you. Thank you. Alright, so the problem was find the Mobius transformation T of Z. You can use whatever letter you want. T for transformation, T for Tim, T for whatever you want. Tasvia. There you go. Alright, so I think I gave you the points. Find the one. We want T of 1 to equal -1. We wanted T of I to equal 0. And we wanted T of -1 to equal +1. And let's draw a picture of what's happening, because pictures are gonna like be really, as you know, I said this ages ago. Ages ago, the pictures are half the fun of this class. So the original points are 1, I, and -1. So 1, I, and -1. Let's call those A, B, and C. And then those map to, and I'm going to call these A prime, B prime, C prime, -1. So -1 is A prime, that's the output. B goes to 0. So that's B prime. And then we got 1. So somehow it's transforming all this stuff into this. Now, one thing we can think about is that these all happen to be on the unit circle, and these actually happen to be on a line segment, or a line, if we wanted to extend it in both directions. We'll talk about what's happening here with the basic geometry, but did anybody solve this and can help us, like, help talk us through this? Okay, fair enough. So nobody has an idea, right? And that's cool. That's all good. Help me figure out, what can I do? What would you do naively? Here's a problem. Putnam exam. Find A, B, C, and D. What do we do?
First plug in 0.
Yeah,
Or plug in I because 0 is equal to
So plug in these points, right? And so that's a good step. So let's just plug in these points. Plug in the known points. And so what we're going to get is -1 equals A times 1 plus B, C times 1 plus D. That actually looks like a pretty nice piece of info. Well, let's keep doing that. Let's put in the I. And then it spits out 0, which is really sweet. So we've got 0 equals AI plus B over CI plus D. And then lastly, we have 1 equals -A plus B over -C plus D. Does this make sense where I'm getting these equations from? Everybody cool with that? All right. So now I have to solve this system. What's some pretty low-hanging fruit here that I could at least simplify right off the bat?
0.
0 is like the lowest of the fruits, right? It's always on the ground. Look for zeros on the ground. Little rotten apples to eat. So what this tells me that the top must be 0. The only way for that fraction to be 0 is for that. Now I've got a relationship between A and B. So that's sweet. That says that B is equal to negative I times A. Cool. So I've got A expressed, or B expressed in terms of A. Let's see what else we got here. This top one says that A plus B equals negative C minus D. And this bottom one says that negative A plus B equals negative C plus D. Take a moment, see what you can find. I'm gonna run to the restroom. Be right back. We have 3 equations but 4 unknowns. We're not going to find a unique solution, right? So there's not a unique solution, but hopefully all the solutions are multiples of each other, something like that. Get like a subspace, a linear subspace of dimension 1. It's the codimension of our solution space. That almost sounds like I know what I'm talking about. Almost. I met someone who actually listens to our recordings the other day.
From Regis?
Yeah, from Regis.
Are they like an offhand or is it just a random person?
No, it's Chris. Hi, Chris from DiffyQ. Chris.
Oh.
Yeah, it's Chris.
Okay.
Because
Why do you
Chris
think I love Chris?
is insatiable.
He knows he's not getting credit for this, right?
He yeah, he might know. He might know.
Oh, okay.
Shh, I'm trying to lead him on. He thinks he's getting credit. Anybody got anything for me here? Or it's like moves or anything? Give me some moves.
Well, firstly, plug in negative AI everywhere for B, because we don't need B.
Okay, cool. Alright, we'll call this 2. So we're gonna, take this top one, so we've got A minus IA, that looks pretty good, right? Equals negative C minus D, and then down here we've got positive AI plus B. Oh wait, no, so that, negative A minus IA, good lord, equals negative C plus D. Those look really terrifyingly close.
Yeah, you add them together.
Add them together. And that's going to cancel the D's, and then we'll have C in terms of A. So we add these together, the A's cancel, we get negative 2IA equals negative 2C. So C equals negative IA. Almost done. We've got, if we know A, we now know B, and we also know C. How do I find D?
Plug in C.
Yeah, but well, how do I isolate D from these two? We can just take these two that you've already done all the nice work in. How do we get D isolated in this? You really saved Sydney and Nathan's lives because the recording stopped. So I don't know how much of this recorded in the first part. But just summarize and just copying down the work that we already did. This was Z minus I over I Z minus 1. Cool. So let's talk more about the Riemann sphere and also Mobius transformations. First thing is I want to tell you about Mobius transformations. Is that we can write them, and it was hinted in that video that we watched, that Mobius transformations are just translations of the sphere, dilations by raising and lowering the sphere, and rotations by spinning the sphere around different axes. So this is a general fact that is not presented in our book, but it's actually very informative, is that any Mobius transformation, so if I have T of Z in the classic form, CZ plus D, this can be written as a composition of translations, rotations, and scalings in the following way. This can be written as BC minus AD over C squared. So that's a scaling right there. That's just a complex number that acts as a scaling, and it can also act as a rotation, as we know. But that is our prime scalar and rotator times 1 over Z plus D over C. So that's an inversion with a shift first, plus A over C. And let me kind of talk about how this might work. So T of Z, how would we get that? So T of Z acts like this. We first find Z plus D over C, and that's the translation. So I'm working my way from the inside out. And then I invert that. And that inversion, that's harder to picture because we're literally kind of taking infinity and moving it to 0 and vice versa. So that invert that quantity. So we got 1 over Z plus D over C. Then take that and scale it. Scale it by this factor, which is also a rotation as well. So then scale, rotate by BC minus AD over C squared. And lastly, take all that and translate it, left or right, or just in some direction, A over C. Finally, translate by A over C. That's it. So it seems pretty simple, but as you've seen, the effect is pretty intense. So that's like fact 1 about Mobius strips. Let's just call that, I'll just call it fact 1 for today. Fact 1. Fact 2 is this. Mobius transformations. I'm using X forms to shorthand transformations, which I could have written 5 times in the process of explaining what this means. Mobius transformations map circles and lines, and I said this in my email, but I want to talk about it, to circles and lines. And even more than that, in the extended complex plane, remember that? This guy here? Circles and lines are the same thing anyway. A line is just a circle that touches infinity. That's all. A line is a circle that touches infinity.
Do you mean like a line that touches infinity up there?
Yep.
Oh,
Yeah.
okay.
On the Riemann, think about the Riemann sphere. To make this like meaningful, think the sphere. because otherwise it just doesn't really make a whole lot of sense. So let me come back to our transformation over here and write that as the composition. So here we have a equals 1, b equals -1, negative I, excuse me, c equals I, and d equals -1. And I'm just going to plug that in to this decomposition here. So this is equal to BC minus AD. So BC, so that's actually 1 minus A times D, which is +1. So 2 on top over C squared, that's just -1. So that'll simplify to -2. And then times 1 over Z plus D over C, and D over C is -1 over I, which is just I. So notice -1 over I is just I, so I'm just going to put plus I there. And then lastly, we've got this, what question? Okay, cool. Lastly, we've got this translation plus A over C, so 1 over I. Well, 1 over I is -I. And let's write that one more time, because this first part's not super helpful. This is -2 times 1 over Z plus I minus I. That looks elegant. Not bad. Let's take a look and see what that does to this shape. Let's take this circle and see what happens when we do all these things to it. So remember, the first thing I'm going to do is shift by I. So this Z plus I says take all your Z's and add I to them. So the very first thing we do, so let's make a little version. This is the unit circle, and in all the guts and everything. And we can even make it, we'll make it the closed unit circle. Closed unit circle. So that's I. Keep these points in mind because they really help. And I had my jollies doing this yesterday afternoon, out in the shade, enjoying the beautiful afternoon. And I couldn't wait to tell you. So, first thing we do is shift by I. And Z plus I just lifts all this stuff up by I units. So it actually moves the circle up. 2I, I, and it just sits, wow, you know. Imagine that was a good circle.
Draw the circle first.
Yeah, that's what I should have done.
The rules.
It is the rules for good circling. So add 2I. Now reciprocate. So this is the part where it gets hard. But remember how we defined 1 over infinity was 0 in the extended plane, and 1 over 0 is infinity. So that means this point at 0 is going to go to infinity. Now I can't, it's not like straight up infinity, it's that infinity out at the edges of the plane, and you can enter it by any direction you want. You can get there if you just keep heading in any direction. So it's a little misleading. So let's take some of the less freaky stuff here. So now we're going to do 1 over Z plus I. And what that's going to do is send 1 over, what's 1 over 2I become? What is that number? So I'm taking this point, figuring out where did that go? Where did it go? Negative I over 2. Does that sound good? Yeah. Multiply top and bottom by negative I, the conjugate of the bottom. Okay, so this point here, let's call that, again, A, and then that went, here's negative I, so that's like right here. So there's A prime right there. And that's negative I. So we're at negative half an I. Cool, let's actually grab a point off to the side and see where these two go. What's this point right here?
1I.
1 plus I. Could you do me a favor and find out what the reciprocal of that is, please? Whoa, dude. What's the reciprocal of that? Simplify. Find that complex number, please.
Square root of 2. Okay.
brain is thinking the right way. Just multiply by the reciprocal though for the easiest. Is that right? 1/2 minus 1/2 I? Yep, cool. So we'll call this B. And so B prime is straight across from this dude just out 1/2 of a unit. So there's B prime. Don't those two look like they're in a line together? Straight across from each other. And let's just do a quick sanity check. What's the point on the other side? What's this dude? -1 plus I. Can we please just show where we think that's going to go? It's always good to do computations like this at least once to convince yourself of all sorts of things. I'm going to make a prediction, but I'm hoping that I'm right. You'll let me know. I believe that's where we're going. I hope. I don't know. Better check because I don't see any fervent nods or anything like that. Two. Yeah, I think that's right. Yeah. So that point C went to C prime, which is straight across in the other direction. So we're starting to get the sense that maybe that circle maps onto this line. Now what's way out at the ends? It's this point at 0. This point here is the thing that gets mapped out on either direction. So as you come in this way, you're moving out this way on that line. As you come in this way, you're moving out that way on the line. And the closer you get to 0 here, the further out on that line you are. Cool, yeah, good. All right. Where is the guts? Where's the inside? And how can we figure that? Where's the guts?
Plug in like I.
Yeah, just take a point from the inside and see where it comes out over here. So what's 1 over I? Negative I. So the guts are underneath. The inside of this thing is down here. So here's the guts. Shade that out. Pretty wild, but see, like if we just calm down and like just, you know, check some things out, it starts to fall into place. So now we've done this. Now we got to do the scaling. What does this scaling do? What does multiplying by -2 in the complex plane do for me?
Does it rotate or flip?
Tell me.
Doesn't it like flip up? And so like the insides are facing up, and then like A would also be at I.
It rotates by 180 degrees and makes everything 2 further from the origin.
Yeah, so it's gonna get, that all sounds pretty good. Yeah, the rotations in the inside out and all that stuff. So if I let's take some points here and just see where they go. Where does -1/2 I go? It goes to positive I. So let's get this over here. And let's write this next part out. So now -2, 1 over z plus I gives, it's going to change the sign of everything. So like, let's see what some points here. So we had 1/2 minus 1/2 I. If we multiply by -2, so I'm gonna write times -2, we get -1 plus I. So that means it takes this point here and moves it up to plus I. Or, excuse me, -1 plus I, so it's kind of like right here. So there is this like flipping this way and a flipping up this way going on. But like, oh, what was that great thing you said about rotation though? So -2 equals 2e to the I pi. Right? And e to the I pi, this is a rotation by 180. So imagine picking up the plane, picking it up and just rotating it 180. That puts this stuff on top. And then multiplying by 2, which does a stretching. So it stretches up this way. So the first thing, let's go check this out again. I really want you to check this out. So if I rotate by pi, the first thing I get is, that's at 1/2 I now. So right, we're taking this and just flipping it. The B prime is over here, the C prime is here, and A prime is like right there. That's just rotating by 180 around the origin. Just take the sucker and spin it, and then scale by 2 takes all these halves, right? Because this is like 1/2 plus 1/2 I. Just scales everything out and up. Scaling by 2 gets us here. Here's I, and it's all this stuff up here. And then here is 2B prime, here is 2C prime. They're stretched in a couple directions. It's changing, it's scaling the modulus by 2. So imagine B, the modulus of B just growing by 2. The modulus of A growing by 2, factor of 2, and then C growing by a factor of 2. You can see, it looks pretty reasonable. Any questions on any of this? I know this is painful and tedious, but it's like so good to like just tear this thing apart. We're almost done because now all we have to do is what? What does this final part do?
Shift it down.
Shifts it down by 1 unit. So that's just a shift straight down. And when I shift this straight down, where do I land? Right on the real axis. So then finally, the last part is -2/1 plus ZI minus I, and this shifts down 1 unit. And then we see that we are right where we thought we might be. And I didn't label that super precisely, but it's just that one right above it shifted down I units. It's this one. Does that sound good? So we can take these things and visualize them, even though there's this crazy infinity stuff going on. We got this. We can work this out. I got one other thing I want to point out to you. I want to really drive home the circles and lines are the same thing for us. So just imagining on the sphere, like here, this is 0 down here, this is infinity up here. It kind of makes sense, right? Just think about on Earth, how we navigate. And we basically pretend like we live on a plane, right? We pretend that we walk on a plane and everything's straight, and it's not even remotely straight. It's not even spherical, but that's in the gross scale, it's certainly physical. So this thing here, one of these great longitudinal lines on the Earth, seems like it's pretty straight to us. It feels like a straight line. There's really no, everything on Earth is a circle if you keep walking far enough. So a circle is just a line that hits infinity. If it doesn't hit infinity, it's a circle. So that's just a big ass circle right there. So that just keeping in mind this picture, circles and lines are identical things, and so none of this is super mysterious. If you try not to think about it too hard. That's the secret, just kind of like get that mathy, like, yeah, that sounds about right. Okay, so, let's see, I think that's about all I want to say about that, but I do want to talk about some other functions. So I'm kind of thinking next week I might give you your like first exam. It won't be like an in-class thing, it'll be a take-home thing to work on. But it'll be a summary of everything we've done. Yes, ma'am?
When?
Next week.
When?
I don't know. I haven't even written it. Why?
I probably won't be here on Wednesday.
If only there was a way to send things to you.
I can take the test.
Or maybe like if you didn't see class later, and you just wrote the problem on the board somewhere at some point.
What? Wait, now I'm confused.
Did
Okay.
you say it was a take home?
It's a take-home.
Oh.
Yeah. What were you were just playing.
Yeah,
Okay.
there's a video, if you just write the problem on the board during the video, then,
That'll work too.
yeah.
Yeah. But I want to make a nice, like, it helps me to write it out in text. I'll gladly send it to you. No big deal. It's not an in-class exam, so it doesn't matter.
Oh, okay, because if it was, I could just take it on Tuesday, maybe.
Yeah, but it isn't. So you'll just be out Monday.
Wednesday. I'll
Okay.
be here till Wednesday.
Got it,
No,
got
I'll be able to do
Cool.
this.
Got you covered.
Thank you.
Okay, yeah, so let's start talking about the other functions. So this was the linear fractionals. This is the, one of the basic operations in the complex plane, relates deeply to the sphere. The rest of this stuff is kind of weird. So some other important complex functions. Beyond the linear fractionals, first one is e to the z. Pretty elementary, like, function for math, right? E is the core of so much of what we do. There's a lot of secrets hidden in this. There's so many secrets hidden here. And that are gonna tie together things. Do you remember hyperbolic functions? Do you remember those? Cosh, sinh,
Oh, yeah.
things like that. You didn't do anything with them except maybe differentiate them or stuff like, I know in my class we didn't do much.
They're vaguely important in some physics.
They are, they're vaguely important, especially in engineering, they're actually important, because the hyperbolic cosine is a catenary, which is one of the strongest structures, available for an arc. But this guy here, let's try to be naive about this. I'm gonna say, oh wait, z looks like that. And then use properties of exponents, assuming that all works well, and it does. What's up? What's wrong? Oh, okay, cool. What's that? It's this guy.
Cosine y plus sine
I sine y, yeah. Let's make sure not to put that
Oh,
y
yeah.
inside there, because then we get a whole new beast that we're gonna talk about, but it's a whole new beast. This is it. This is our definition of e to the z. This is how we work with it. Not bad at all, huh? Not too bad. Let's see. Are there any things we want to do with it? Yeah, I want to make some notes about it. Notice that it's a periodic function. So our exponential function is periodic along the imaginary axis. So as y changes by periods of these functions down here, aka multiples of 2 pi, the value remains the same. So in other words, e to the x plus I times y plus 2 pi k. So I've got y plus 2 pi k times that whole I there. That's just e to the x plus iy for all integers. So that's interesting because that tells us that we really just need to understand like a band's worth of e to understand the whole of e in the complex plane. So let's make a note though here that e to the z is periodic with period 2 pi I. So it's got an imaginary period because I'm adding multiples of 2 pi I, really. Periodic 2 pi I. So in other words, if we're in the complex plane, and we have maybe say this goes up to pi and this goes down to minus pi, that whatever happens here just gets cookie cuttered for the rest. So once we know a period's worth, we know everything. We know all of C for e to the z. Good. Let's see what other fun things we might have to. I don't know if I have a whole lot. Let's actually do a couple, like just an example. So if I asked you to find e to the -1 plus pi I, you would break it apart. You would do it as e to the -I, e to the pi I, and you've actually done this a lot, right? This is just rotational. This is just the rotation part. What is e to the pi I equal to?
-1.
-1. So this is just -1 over e. So it's actually a real value. And it won't always be a real value. It depends on where you're pointing into the complex plane, what your direction is. So it's not hard to actually think of an example where the value of this would be imaginary. Let's get some new functions out here. This is great. Then we can spend Thursday. Did you hear us out?
Yes.
Okay, it wasn't just my head. Cool. Let's make sure we're still recording here. Yay. Let's define some other things. I would also say C, and I'm not going to write this up here, page 56, proposition 3. I did order a new copy of the book, by the way. I ordered the most recent edition. It should be here this week. Can we just check to make sure? Someone please check.
It's on 50. It starts on 55.
On 55, thank you.
Yeah.
Thank you. Soon I'll be with you. I guess I could look at the digital book, but I guess I haven't. So, trig functions of complex numbers. So we've got sine of z, and we're going to define that. So I'm using this colon equals as definition. I'll just write def there for the first time. Is 1 over 2i e to the iz minus e to the negative iz. Now look, we're tossing an extra I into the z. So you take your z, multiply it by I, then do that. And we'll get into like why all these things are in a bit, but let's just kind of keep going first off. Cosine of z, cosine of z should be the derivative of that. If calculus is holding true, and it's freaking better. Let's just pretend we know how to, that we can differentiate this and everything's kosher, and that this function is entire, which it is. What's the derivative of this with respect to z? It's nice to shut up for a while.
Yeah.
Did you get an answer now?
I do have an answer.
What did you get?
1/2 EVIZ plus e to the negative IZ.
Beautiful. Yeah? Any questions on that? Let me know. Let's just check to see that these things work in the real, that these are just extensions of what we already know. Check if z is just x plus 0 iy, right? So, or just 0 I don't need the 1. This should look like sine. So let's just check it out. This is equal to 1 over 2i e to the I times x minus e to the negative I times x, right? And that's just a real number, like so. And so we've got 1 over 2i e to the ix minus e to the negative ix. Where can I go from here? How can I convince myself that, yeah, that actually is just sine of x?
Eric,
Ba?
can you expand using EVI something equals cosine something plus
Yeah,
I?
let's go to that definition. Yeah, beautiful. Let's go to, you were about to say something too, Lou. Were you gonna say that? Or maybe you weren't, and I'm just projecting, whatever. But we know this, right, friends? Don't forget. This is always a truth in the universe, especially the complex universe. So this is like as important to us as the Pythagorean theorem is everywhere. Right? This is a fundamental result. So I can use that here, and this is 1 over 2i cos x plus I sine of x minus cos of negative x plus I sine of negative x, because now I'm just using negative x here for the theta. And then this, let's keep going through, that's 1 over 2i. Cosine is an even function, so this is just cosine of x. And this is negative sine of x because sine is an odd function. So this is 2 cosine, oh no, whoop, easy buddy. That's cosine minus cosine, they're dead. And then I've got 2i sine of x. And look at that. Yay. So our sine is just a pale shadow, just barely any part of the true full sine function. Sine function is a glorious thing that extends over the whole complex plane, and when we settle down to the real line, it's pretty useful, but not as glorious as the whole blossom. Any questions on that, my friends? Can you tell me what happens if I have a pure imaginary? So what if z is 0 plus iy? Can you tell me what that turns into? You might want to write, because I think doing this by hand could be a little painful. So what if z equals 0 plus iy? And then once you get it, tell me if it reminds you of anything hyperbolic. Let me put a couple old friends up here. These are lovely functions. These are real functions. Real valued flashbacks. Get it as simplified as you can, and see if you can find something involving these. I guess we're just doing sine here. So. Very clear. You back on the road, Grace?
Yeah.
Oh, so nice.
Good.
You're good, awesome. Good, good. You got it.
Yeah, I think so.
Yeah, beautiful. Yeah, that's lovely. I was thinking, I have negative, but I think this looks better.
Well,
yeah.
-1 over, or negative I over
See,
negative
these
one.
are these are backwards though.
Are they?
See what I'm saying?
Oh, no, but there's an I of y.
Right. But this is e to the negative y minus e to the
Yeah.
y.
Okay.
But that's the reverse of, that's negative
I forgot to
sinh.
factor that out.
Yeah.
Now we do that. Okay.
Like so, yeah. And then this, if we pull out this I, we can actually, I on the bottom becomes negative I on the top, right? You can move an I from the bottom or the top, just gotta change the sign of it. And then this is negative I times 1/2 e times negative 1/2 e to the y minus e to the negative y. You need to, if you're matching up there with hyperbolic sine, notice how it's e to the positive exponent minus e to the negative exponent. So this just turns into a good old fashioned, oh, you know what, Noah, I think you were right.
I was right.
You were right, yeah.
Ew!
I did pull out the negative.
Yes, you did.
Someone stuck a gum under my table.
Oh, well,
Why were you exploring?
yeah,
other
honestly,
people?
I mean, seriously.
Like, that's not your fault, but also,
I can't believe what I found in this toilet.
Oh, you might have.
What is up with the world? Alright, so in other words, here's a neat little thing. I don't know if it's, I guess it's an identity of some kind. The sign of IY is I hyperbolic sine of Y. Kind of prove that for all Y that are real. So we've got like this beautiful identity here that links together these wild hyperbolics with just the with the complex trig functions. So like when I talked about these in class, if you were in my calc class, I went off about how these were just fragments of the whole. And now you kind of get to see where they're coming from, like how they sync up with the true ones. And I think we're done for today. And I want to come in and talk about the natural. Here's what you can do to prep for Wednesday. We're going to talk about the complex logarithm, which kind of takes like a whole day. I think that's definitely a full day of class because it gets very complicated. So if you could please read section 3.5, that would be great. So read section 3.5, friends at home, please. And let's call it. Yes, Labina. What's up?
Oh, okay. Yeah, that makes sense.
Oh, wow, that was easy. You just need that interaction for your brain to like jump back on. Cool. Awesome. Thanks everybody.